So first of all, apologies for this. We tried to do it during the break. Somehow it didn't work. Now it works. Now it's the other way around. And thank you very much for organizing this event and inviting me too. Yeah, so it's a pleasure to be here. So I will present some optics thing. In fact, I was thinking maybe I should talk about cold atoms and lattices and stuff, but Gediminas told me we have enough cold atoms and lattices, and we don't have enough optics, and I'm very happy to talk now because there were a couple of related talks before, so I can really go fast and not take too much of your time. All right, so now so I'll try to tell you about single photon sources using Rydberg atoms, EIT, and pretty much the stuff you have heard already. The question is how to produce single photons. Okay, so that's say my motivation to do this. So one way is to take a single emitter, excited to excited state with a laser, and we can do it pretty easily, and it's sort of and with high probability fidelity or efficiency. Yeah? So for example, you apply a pi pulse, or you chirp this pulse. So you can so let's assume we can prepare with a single with the probability one the single emitter in an excited state. But now we want to emit this photon. We now want to convert the single excitation into a single photon, but not propagating in all 4 pi directions, but in a well-defined direction. So what we have to do, we have to put it in a high Q cavity, not necessarily high Q, but the coupling of this emitter on a transition that we want to emit a photon should be strong to the cavity, much stronger than basically the spontaneous decay rate, which defines the probability of emitting into all 4 pi. And then we can produce a directional photon. Yeah, but now it's difficult, so I don't want to use cavities. All right. The other possibility is to use this Duan-Lukin-Sirac-Zoller scheme. And this is sort of a probabilistic scheme, but it works. You already know how it works, okay? So you shine a laser, so you have a collection of atoms. Now we're talking about that atomic ensemble. So it's a large atomic ensemble with large optical depth. You shine a laser onto the atoms, maybe detuned, weak laser, and then you wait until a spontaneous Raman photon is emitted in a predefined direction. And you put a detector here, and when your detector clicks, you know that there is a single spin flip in this atomic ensemble, and it's coherent. At least it's a phase match to this direction. Yeah. So this is probabilistic because you want to make sure that no more than one photon is emitted here. So you typically use weak pulses and low probability of this event. So it's sort of heralded event. So whenever the detector clicks, then you know that there is a spin wave here, and now you can convert the spin wave with this read pulse into a single photon propagating in the phase match direction. Okay, so this is a probabilistic scheme. And then the other scheme you already heard from Tilman-Fao, and so that's to use sort of combine the ideas of a single emitter and a large atomic ensemble, and that's basically you take a large atomic ensemble, you put all the atoms in a small enough volume, but you still make sure that the optical depth is large. Then you can excite any one of the atoms to the Rydberg state, and because of the Rydberg interactions, you cannot excite 2 or more atoms within this volume, provided the volume is small enough, so you have this full Rydberg blockade. And this you call a superatom. And so once you created such a Rydberg excitation, then you can apply another like a control pulse or driving pulse, whatever you call it, and emit a single photon into the phase match direction. Okay. Now this requires full blockade to create a single photon. Okay. So, so all of them are good, all of these schemes are good, but I want sort of to combine the best parts of each scheme and come up with something, I don't know if it's better or worse, but something new, let's say. Yeah? And that's what I do. So, so the idea is that, again, we can prepare single emitters with high probability, single atoms in an excited state. Yeah? And that's what I do. Single atom I prepare in the excited state. Now I don't want to use a cavity, all right? So instead, I want to transfer this single excitation, now it's sort of a deterministic single excitation, to a large atomic ensemble using some long-range interaction. Yeah? And by transferring it, I create a spin wave, a delocalized spin wave, in the large atomic ensemble. So I don't create the spin wave in the ensemble, I transfer the single excitation to the ensemble, okay? And for this, I will use a long-range dipole-dipole interaction between the Rydberg states of atoms. So, and then on the third, and now I have this well-defined spin wave with well-defined phase in a large atomic ensemble, and I can use this TLCZ protocol sort of and emit it, or like stop light for the IT business, and emit it into the phase match direction. Okay, so that's the general idea. And let me just quickly now explain the details of it. Yeah? So this is my single emitter. I excite it from the ground state to some state I call up. It's highly excited Rydberg state. Yeah? And so my initial state is sort of, I have a large atomic ensemble, all the atoms are in the ground state, and then I have a single emitter excited to the single atom excited to the Rydberg state. On the next step, what I do, I use the dipole-dipole exchange interaction on the Rydberg transitions between the single emitter and the large atomic ensemble to transfer this excitation, basically, or map this excitation onto the Rydberg excitation or spin wave of an atomic ensemble. To do this, of course, I need a laser which drives the atoms from the ground state to some intermediate Rydberg state, and then the dipole-dipole exchange here. So I make sure that this laser is detuned, so that if there is no single emitter, so no atoms can go up and get excited. So it's just basically dispersive interaction. But now, but then it's sort of a two-photon resonance, or near two-photon resonance, one photon coming from the laser and the other one coming from the exchange interaction. Yeah? And to make sure that this process happens with fidelity or probability or efficiency 1, I chirp this laser so that I have adiabatic rapid passage from the ground state, collective, all the atoms in the ground state, to a single collective spin excitation state of the atomic ensemble. So I apply a pulse, this laser pulse, with few microsecond duration, and I chirp it so that I start with some negative detuning, I end up with some positive detuning, and then what happens is that I produce one spin excitation here, which looks like this. In fact, it looks like this. Yeah, this is a numerical simulation, and this is just a cartoon. And the shape of this excitation is exactly the dipole-dipole exchange shape, which is C3 over R3, 1 minus cosine squared theta, whatever. Yeah. So I produced this spin wave. You have seen it in the previous talk already. The phase is well defined. It's long, so it's several, maybe 10 or more microns long in an optically dense atomic ensemble. So I use about 1,000 atoms here. And then I can, on the next step, then I can apply this retrieval pulse, and this spin wave is converted. So something happened here, sorry. So the spin wave is converted to the single photon, okay? And this single photon is, in fact, is emitted in a narrow solid angle, and we can have a very high probability of emission of this single photon in the narrow solid angle versus the 4 pi emission if we use many atoms. Okay, so in this particular example, I used about 1,000 atoms in a trap, in a Gaussian trap, which is which is a few micron cross section and about 10 micron length. And so what I get is that I get more than 70% of all radiation is emitted in this predefined direction, and the rest is emitted into the 4 pi, so I can define the efficiency like this. So this, and basically it's sort of a universal formula. So if you want to define, if you want to emit into the solid angle, this delta omega, from the ensemble of n atoms, then the efficiency is going to be n times solid angle divided by 4 pi, and 4 pi is basically is where the rest of radiation goes. So the radiation goes into the 4 pi. And this eta, this small, it's some parameter which basically defines this participation ratio of all the atoms. If you have all the atoms excited with probability 1 over square root of n, 1 over n, with the amplitude of 1 square root of n, then this eta would be 1, okay? All right, so so that's exactly what happened now. So this is the radiation, this is the spatial profile of the radiation emitted, and it's emitted, of course, within a narrow EIT line width here, the inverse of this. The whole process can be repeated. So you can excite the atom again, and then so something happened here. Sorry, and repeat this process over and over. So you have a deterministic source of single photons, or nearly deterministic source of single photons. Okay. Better still, okay. The same idea has appeared a few months earlier in, or maybe more sophisticated version of this idea appeared a few months earlier. In the group of Petrosyan, and so the idea is the following again. But so the application was not that much the single photon emission, but the state transfer between qubits. Now, instead of this random ensemble of atoms, they proposed to use an array of atoms with a sub-wavelength distance between them, and maybe 2 or 3 layers of such atoms, and then. By mapping, or again transferring the single excitation of the qubit to such an array in a controlled way, so that you can shape the spatial distribution of the emitted radiation by tailoring basically your driving field, the field that maps that helps you with the dipole-dipole interaction. So this helps you to induce the dipole-dipole interaction mapping from the source atom to your phase array. You can control the amplitude and phase of every atom in this array, and by doing that, you can basically control or tailor the emission pattern of your radiation. Of course, this is experimentally more challenging because, again, your laser field has to be modulated on the range of single atoms, and atoms should not move. But then you can control also the and so this is the scheme from their paper. It's pretty much the same as I introduced before. Okay, so I'm doing with time. Okay, good. So so that's the sort of the first idea. And since I have more time, I will tell you something related. Okay, something related which sort of happened even so. The idea came out earlier, and then okay, so whatever. How to, so basically the idea is about, you have heard already about EIT with Rydberg atoms, yeah? So I want to do something a little bit different. I want to replace the driving field in the EIT by the dipole-dipole interaction between the Rydberg atoms, yeah? And this gives you new physics, okay, funny physics. So let me remind you again, just on 1 or 2 slides, what is DIT? If you have an atomic ensemble, many atoms, and you, so again, something happens all the time, sorry. And then you drive these atoms by a resonant laser, or you probe these atoms by a resonant laser, then you have this absorption profile for a laser, which is a Lorentzian, of course. So the susceptibility, the medium susceptibility looks like this. So the imaginary part of this is a Lorentzian. Yeah, so this is supposed to write the imaginary part. Now, if you couple this excited state to a long-lived state, and in this particular example, I assume it's a high-lying Rydberg state, with a coherent laser, coherent resonant laser, then it splits your susceptibility, it splits your dispersion, your absorption profile into sort of 2 Lorentzians out of phase, and so at 0 point you have exactly 0 absorption, and there you have some line width of this EIT, which is basically determined by this driving field square divided by the decay rate. Yeah. And so when you send a pulse or a probe pulse in the medium, so and then what happens upon the entrance into the medium, the pulse slows down because it forms sort of a coherent excitation, coherent superposition of the photonic and atomic excitation. Yeah, so which looks like this. We like to call it dark state polariton because it does not contain the intermediate atomic state. And the group velocity is small. It can be slowed down all the way down to 0 by simply changing this mixing angle, and that means the turning off this field, this driving field. Yeah. So that's the essence of the EIT. And now let me do a little trick. Let me replace this driving field in the EIT by a dipole-dipole exchange interaction. Now this is supposed to be the same atom I was showing you before. Yeah? So by the driving field, let me replace the driving field by a dipole-dipole exchange interaction with something. And this something is another Rydberg atom, which is sitting outside of your atomic ensemble. And because the interaction is really long range and strong, and I'm talking about the highly excited Rydberg states where the dipole moment is enhanced by n squared, so n is a principal quantum number. So we can have a megahertz or tens of megahertz interaction, exchange interaction strength on the distances of microns. Okay, so this atomic ensemble can be really 10 or 20 micron long, much longer than if you would use for the dipole blockade. Yeah. So and then put one or more sort of these spin atoms, I call them, and induce the transparency for the prop field. Of course, again in this scheme, I again assume that I have some auxiliary field, a laser field, which bridges this gap from this state up to the Rydberg state. And then let's see what happens. So in the usual EIT, every photon that enters the medium and wants to become a dark state polariton, it has to take one photon from the driving field. Now there is no driving field here, so instead it has to flip the spin atom to go up to the Rydberg state. So that's the idea, okay? So now if I have just one atom in the Rydberg state here, and I send one photon, then this one photon can propagate in this medium, which is now transparent, by flipping the spin. But if I send but while this one photon is inside of the medium, the second photon basically, as it wants to enter the medium, it cannot create dark state polariton because there is no spin atom to take for the driving essentially. Yeah? So that means that this dipolar exchange-induced transparency can exist only for the number of prop photons not larger than the number of spin atoms. So the most practical case, of course, we are talking about a single atom in here. So that means I will have sort of a transparent medium for one photon at a time. But when I send two or more photons, they will have to be absorbed because they are just seeing a two-level medium. Okay. And this is basically the spatial profile of the medium susceptibility, and this is a now operator valued function because it is determined by the state and the number of my I'm almost done. Yeah, so a state and the number of my spin excitations in the medium. Yeah, so and moreover, it's also the photon number dependent. Okay. So the group velocity also depends on the photon number. I think, I summarize. So what I tried to show you that strong long-range dipole-dipole exchange interaction between the Rydberg atoms can be used for something useful. For example, to couple a single or few atoms to a large atomic ensemble. And by doing that, I can foresee an efficient probabilistic source of single photons by transferring the excitation of a single emitter to a large collective atomic excitation, which can be then emitted into the phase match direction with high probability. And then, moreover, if we do a little bit more sophisticated thing, if we arrange atoms in an array, this array can play a role of phased array of antennas. Of course, we have to control now individual atoms to a good degree, the amplitudes and phases of individual atoms to a high degree. But then we can even shape the spatial profile of the outcoupling radiation and send it between distant qubits. This is the paper from the Zollers group. And then I showed you also what is the dipolar exchange-induced transparency. Basically, I said, let's quantize the driving field of the EIT. And one way is to put, for example, the atoms in the cavity, and then the cavity mode can play a role of the quantized field. This such ideas, cavity-induced transparency, I didn't show you, has been around for a while. There were experiments in MIT already some years ago. But on the optical transition, now I say, okay, let's go to the Rydberg state and use the for such a quantized driving field, use another species of atoms, or a single atom, or few. Yeah? And then you can induce sort of the transparency in a quantized way. So you have transparency for 1 or 2 or 3 photons, but not more. Yeah? And this system can serve then as a photon number filter or transistor. Yeah? Yes, and now I want to advertise my own poster before you ask me questions. So that will be about a different topic. Thank you very much.